New breath, I feel the grip releasing, scraping my guts off of the ceiling. I got that sunny bunny feeling. Making time, breaking ground, sail brown day to chocolate town. Making time, breaking ground, sail brown bay to chocolate town. Making time, breaking ground, Greyhound bus to chocolate town.
All right, so this week you'll be working in your lab in your hack on functions and pass by reference and pointers and everything like that. But in lecture, we're going to start on the next module, which is arrays. And arrays are a way to deal with more than just one piece of data. In fact, it's rare to deal with just one piece of data. One name or one number or one score or something like that. You need to deal with collections of data because you're going to be processing large amounts of it. And you need to be able to store that data in a collection. In C, we call them arrays in order to deal with them. Just a second. There we go. All right. So what are arrays? Well, arrays are just in, sorry, not in Java. Here we go. In C, data is stored in arrays or stored in arrays, right? Arrays are collections of similar types of data. So for example, you can have an array of integers. You can have an array of doubles, but you cannot have an array of integers and doubles at the same time. There are some languages that support that, mostly dynamically typed programming languages like PHP, JavaScript, Python. But our arrays in C, they're only one type, right? So you have a homogeneous type here, right? So similar data. In general, arrays have a single name identifier, right? Just like variables, if I say int number of students or something like that, that's its identifier. An array, everything in the array will have the same identifier. To access individual elements in an array, you use an index, right? What is an index? An index is a number ranging from 0 up to n minus 1, where n is the number of elements in the array, right? We call this zero indexing. This is referred to as zero indexing, right? And the vast majority of programming languages, in fact, I only know of maybe one or two that don't follow this convention. The reason that we have this convention is because of how memory works. We'll cover that later on, but basically you are looking at a memory address. If I've got an array of 5 elements, they're stored in memory contiguously all together. So the array is actually a reference to whatever is in the memory. And the 0 is referring to an offset. So if you look at that memory address, it's right there. You don't need to go anywhere else. 1 is 1 away, 2 is 2 away, etc. You've seen this before with argv, right? Command line arguments. The first one is at argv sub 0. The second one is at argv sub 1, etc. So for example, suppose we have an array, called ARR, right? I'm not going to get fancy. ARR is just short for array with, say, n elements, right? Then the first element is at ARR sub 0. That's how we read that. ARR sub 0, that's the first one. It's the 0 indexed one. And notice here that as you've seen before, we're using a square bracket notation. The second is at ARR sub 1, right? Dot, dot, dot. The last is at ARR sub what? If there are n elements in there. Remember, because we're starting at 0, if there are 5 n elements in there, it would be 0, 1, 2, 3, 4. So it's always going to be 1 less than the size. Okay? So if there are n elements in that array, then it's at n minus 1. Okay? Let's just go ahead and get started with an example immediately. Arrays in C, right? And in particular, static arrays. I'm going to show you static arrays just to get used to using arrays, but we're immediately going to not use them anymore and use what are called dynamic arrays instead. So static arrays in C are allocated on the stack. They exist in a single stack frame. So let's go ahead and look at an example. Right? Over here, what I'm going to do is I'm going to create an array that can hold, I don't know, 10 integers. Right? And the way that I'm going to do that is int ARR. Now, if I just did this, right, this is just one integer, right? What I want to do is I want to specify that this can hold 10 integers. So I'm using that same syntax there at, at declaration to use the square bracket syntax to indicate how many you want in there. If you wanted 100, it would be 100. If you wanted 1,000, it'd be 1,000. Let's start out small and see the limitations of these things, and then we'll look at dynamic arrays. All right, so before we go on, what's stored in ARR as of right now? All right, let's find out. Here's that, again, why we call it an idiomatic for loop. You start I at 0. Why? Because indexing starts at 0. I is less than 10, I plus plus. You go up to, but not including that last value. So you're going to end up going up to 9 with this idiomatic for loop. You're going to iterate over each and every single one. Printf, ARR sub %d is equal to %d and the line. I'm going to print out the index I, and I'm going to print out the element ARR of I, sub I. So it doesn't have to be hard-coded to 0. It doesn't have to be hard-coded to 1. It can be a variable. And now you also see why we use I. Why? It stands for index. Right? And this is an idiomatic for loop here. Predict. What is it going to print? Nothing. Oh, it'll definitely print something, but what values are stored in there? Right? Let's find out. Right? Just random values. Right? If I were to run this over and over again, I would get, indeed, for some of them, it's going to change over and over and over again. Why? What's in there? If I were to just create a regular old variable, int x, what's stored in x right now? Who knows? Question mark. Dead beef, right? It could be garbage. Well, guess what's stored in this array? Garbage, right? So if you want to initialize variables, you need to make sure that you're doing that up front. Let's go ahead and set each value, ... And I'm going to steal this code here. And instead of printing the values, let's go ahead and set them to, I don't know, I plus 1. So I'm going to set the first one to 0 plus 1, so that gives me 1. The second one was 1 plus 1, so that'll give me 2. 1, 2, 3, 4, 5, all the way up to 10. Let's print them out again. And let's clear this. And let's run it again. And you'll see up at the top here, again, it's garbage because you haven't initialized it. But then down here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, after you've set each value. Right? So some observations immediately. Right? There is no default value defined for uninitialized array values. Right? Garbage, dead beef, etc. Right? You can iterate over elements in an array using remember, idiomatic for loop, right? And I'll go ahead and make sure that you've got this over here. Right? Here's an array that can hold 10 integers. Right? All right, great. Let's visualize this now. Right? Before we move on and look at something else. Here's that Python tutor visualization tool. Now I've set this up so that it's not too big, right? I don't want a huge, long array here to be displayed on my web browser. So I've only done 5. we go through and set it equal to 1, 2, 3, 4, 5. The things that I want you to observe about this are, well, first of all, where is this array allocated? It's right here in the stack frame of main, right? It exists in a stack frame, and it exists in the stack. Now remember what we learned about the stacks and function calling, function calling, function, right? Each time you have a function call, a new stack frame is created on top of the stack. So if this were located in another function, and I had an array inside that stack frame, when I return back from the calling function, what happens to that stack frame? Popped off and thrown away. What happens to the array inside that stack frame? It gets destroyed. Right? So already we're seeing some limitations here. I can create an array inside of a function, but it can't exist outside that function, at least as far as we're concerned so far. Right? So next. Right? If I were to try to access this from another function, I would not be able to do it. Okay? All right. Well, what's another potential issue here with respect to static array? Oh, first of all, before we do that, what if I wanted to hold 10 doubles? Right? What would change about this? Double. Right? Now it holds 10 doubles. What if I wanted 10 characters? It would be char. That is a string, and that's what we'll be talking about after arrays, because strings are nothing more than arrays of characters. Okay? Let's go back. All right, there we go. All right. What I'm going to do is I'm going to set this up so that I set the first one, array sub 0 equal to 42. Array sub n minus 1 is equal to 101. There we go. What I'm going to do is I'm going to put that value into a variable here, n. Okay? Why? Because, well, what if I just had array? Like, let me go ahead and erase. I've forgotten now how big my array is. And I want to, write code to print elements in the array, ... How do I go about doing that? For int I is equal to 0, I is less than. Because I put it into a variable, what do I write here? N I++. And then I can go ahead and print out the variables in that array, the variable values. What if I didn't put that into a variable? Is there any way to write code to recall how big the array is? No. That's called bookkeeping, and it's something that we're going to have to make sure that we take care of later on in our program. All right? So there is no way to determine the length or the size of an array in C. You have to store that in a variable, and you have to refer back to that variable every single time. All right, well, great. There's n. I'll go ahead and change that. You can actually do that as well. And let me go ahead and print these out. So the first and last elements are going to be %d and %d and line. And let's make sure that this actually works. Array of 0 and array of n minus 1. There we go. All right. GCC. Run it again, and it all works, 42 and 101. Let's go ahead and set up another value. ARR sub n is equal to 200. Right? Now, should that work? Remember, there are 10 values in this array. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If you try to access the 11th element, the element at index 10, what's going to happen? Let's find out. ARR sub n is equal to %d and line ARR sub n. We're probably not even going to get to this point, but let's go ahead and try it. It works. Right. Okay, fine. What if I tried, I don't know, 100? Right. Remember, it's only of size 10. Right. Let's go ahead and try that again. Garbage. I was able to do it somehow, but garbage results. Okay. What if I did something like this? Now, where does indexing start again? At 0. Can you go negative? Let's find out. Well, apparently you can, but it's garbage. Right? What can I go like way beyond? Is that 1, 2, 3, 1, 2, 3, 100 million? Away. Let's find out what happens then. Segmentation fault. So the takeaway on this is if you've got an array of a certain size, that it looks like this, right? That everything is stored contiguously, and you try to access something beyond the bounds this way or something beyond the bounds this way, bad things will happen. Garbage results, right? Segmentation faults. You may end up screwing up your own memory, right? So don't access elements outside the bounds of an array. Is the compiler going to catch this? Let's turn on all the warnings. Find out. No. It doesn't care that you are messing up your memory. That's the operating system's job, not the compiler's job, right? So accessing things outside the bounds, don't do it. Accessing invalid indices will lead to, or may lead to, I should say, because there's no predictability here, garbage results, segmentation faults, right? Or just generally undefined behavior. Undefined behavior in C is terrible because anything can happen, including your entire hard drive being deleted or something like that. That's an extreme example. That will not happen. But undefined behavior is undefined. It's just undefined. Anything can happen, right? So you do have to be careful there. Right? All right. So let's not do that. Right? But let's go ahead and set the first one and the last one. When I've only got 10 elements, that's fine. When I've got 1,000 elements, that's fine. All right? Because how many bytes does an integer take? Do you remember? 4. So 4 times 1,000, that's 4,000. That's only 4 kilobytes. Right? Everybody's computer's got 4 kilobytes. Let's go up to 1 million. 1 million times 4 bytes, that's only 4 megabytes. Everybody's computer's got 4 megabytes, right? So let's find out if this works. It still does. Okay. Let's go up one more. So I just added 1 0 there. That's 10 million, right? Yeah. That's 10 million integers. Times 4 bytes each, that is how many bytes? 40 million bytes. Tell me how big that is, roughly. 40 megs? 40 megabytes? Just short of it? Everybody's computer has 40 megabytes, right? I mean, it's 2023, right? Everybody has that much. This one doesn't. Right? Why? What's going on here? Remember that this is being allocated in the stack. Right? So do you remember what happens if you've got function calling function calling function calling function? You're creating more and more stacks, the stack frames. Now, I only have one stack frame, but what am I trying to shove into this one stack frame right here? 10 million integers, right? Your stack is limited to a certain amount of memory. What happens when you get to the top of your stack, you've filled up your stack, and you try to put something else on top of it? You get a Stack Overflow, right? That's where that website gets its name, Stack Overflow, right? So let me show you on this computer. I think it's ulimit A. There we go. Ulimit is user limit, so it'll tell you all the limits of the resources that you have on the CS50 IDE. For example, stack size. In kilobytes, you only have 8,192 kilobytes. Pull out your calculators and realize that that's 8 megabytes. That's why we were able to get away with 1 million integers, because 1 million times 4 is less than 4 megs. This is 8 megs. It's limited to 8 megs. So when we try to do 40 megabytes, obviously we're hitting that limit and far exceeding it, and we're getting this segmentation fault, right? Because we have overflowed the stack, okay? So that is very limiting, right? Since static arrays are extremely limiting, I'll say limited, right? They are allocated on the stack, which is limited to, say, 8 megabytes. It could be 4 megabytes. It could be, if you're on an embedded system like an Arduino, where you don't have that much memory at all, it could be kilobytes. Right? You do not want to abuse the stack space. You cannot or should not abuse the stack space to store data. even moderately large amounts. Right? Small amounts like, say, 10 integers, no big deal. You can go ahead and do that. In fact, here's another way that you can declare an array. Here's alternate syntax. Alternate syntax. Right? If you know exactly what you want to put in your array right up front, for example, the first, say, 10 primes, or int primes, there we go. All primes are integers. You can use the following curly bracket notation. So help me out. What are the first 10 primes? 2, 3, 5, 7, 11, 13. What am I up to? 6, 17, 19. What's next? 23, 24, 25, 26, 27, 28, 29. There we go. Is that all 10? 1, 2, 3, 4. 1, 2, 3, 4. Yep, there we go. All right. Let's go one more. What's going to happen here? The compiler is dumb. It was not able to detect my errors before of going out of the bounds, right? But it can definitely do this. Why? Well, it can go through and count up the number of commas. That tells you how many elements are in there. And it's saying that I'm trying to fit 11 things into an array of size 10. By the way, it's not an error. It's just a warning. You can go ahead and screw up your memory if you want. Be my guest, is what the compiler is saying. Right? But obviously, you should adhere to those warnings. So we can't do that. What happens if we go the opposite direction? I said that this is primes and that there are 10 of them. What if I only gave it 9? That's fine. That fits within the bounds. Right? Oops. Ooh, no. I lost my... I'm not sure what the quick key is to get rid of that, but whatever. GCC demo.c. Right, there we go. Now the warnings go away. Right? But I'm storing 9 things in it. What's in that 10th thing? Let's find out. 4 int I equals 0. I is less than 10. I plus plus. Printf primes sub %d is equal to %d and the line I and prime sub I. Right. Oops. A dot out. There we go. So 2, 3, dot, 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 all the way to 23. Oh, it's 0. Now, I'm crossing my fingers here. It's not necessarily going to be 0 every single time, right? That's probably just the compiler doing my some magic for me, right? There is, I don't believe that there is a predefined standard that says it should be 0, right? But I've got room for one more if I wanted to add it, right? Likewise, what if I took out, I don't know, 17? Does it fill it in with that 0 knowing that I wanted every single prime? Absolutely not, right? It's just going to have 2 zeros at the end now, probably, right? So let's undo. Oh, I'll keep that. What's next prime? 29? There we go. All right. Okay. Well, again, compilers are dumb, but they can count up the number of commas and see that there are 10 things in there. That means that you can use this little trick called elision. And I'm mentioning that as your 50-cent word for the day. If you elide something in speech, in plain language, in English, right? Every language does this. It's not just unique to English. What you're doing is you're taking out unnecessary syllables so that you can speak fast, right? For example, where'd you go to lunch today? Where did you go to lunch today, right? I elided that into did ya, right? That's what elision is, right? And it's very common, but it's very, very difficult for non-native speakers learning a language to understand the elision, right? Because you're speaking, you're speaking really, really fast, and you're taking away the syllables that you learned, right? And it can actually be quite difficult. But in programming languages, just like regular normal languages, we also have the same concept. If something is unnecessary, you can elide it away. You can throw it out, right? And so the compiler is able to see, okay, well, I can count up the number of commas. That means that you wanted 10 things in there. I can go ahead and fill in that 10 for you. You don't need to provide it. And it'll work perfectly fine. GCC, there we go. A dot out. There we go. All right. Just a little elision trick. And here's the word elision. I think that's how you spell it. Elision. Yeah, there we go. Elision. Okay. All right. So you cannot abuse the stack space, right? The stack space is very limited. Instead, you need to create dynamic arrays. Right? I want to store the first billion primes. Right? I'm not going to write them all down, right? But I want to do that. So we need something else. Now, if you remember, there are two things in this visualization tool that I've got here. The stack, which we're well familiar with, and something called the heap. Now, before we describe these things, just think about what comes to mind on these two words. A stack, what comes to my mind at least, is that stack of dishes. Very organized stack of dishes, one plate on top of the next, right? Very organized, very neat. What comes to mind when you think about a heap, though? Still a pile of stuff, but is it organized? No. Laundry, exactly. That's the classical example. What do you do with your laundry? Well, if you do it properly, you put it into a basket or a hamper, right? But no, if you just have a laundry corner, what do? You just keep throwing clothes on top, right? Some of them stay at the top. Others, because when the pile gets too big and disorganized, they fall down to the bottom, right? But it's just a heap of clothes, right? Or a heap of garbage, right? You just start throwing stuff on top of the heap. It is far less organized, but it is much bigger, right? And that's what we mean with these analogies that we take from regular old language to describe things. All right, so dynamic arrays. Dynamic arrays are allocated on the heap space, memory space, instead of the stack. Right? The heap is a much less organized memory space, but it is much larger. Right. Let's come back over here to code spaces, and let me repeat that ulimit command that I gave it before. All right, there we go. All right. And there we go. There's the heap space. What is my limit now? Unlimited power. Now, it's not going to download more RAM when it runs out. What unlimited means is that you can request as much as you want. The second that you run out of memory, that's the end of the show. Right? Now, you can have more than just the RAM. In fact, when RAM fills up, it starts persisting stuff to the hard drive, which is a lot more expensive because it's now a lot slower, because now it's a mechanical thing. Or if you, what are the hard drive, the bubblegum hard drives? And what is it? NVMe? Okay, NVMe drives, they're not mechanical, so they're much faster, right? It's kind of like flash, but it's faster than flash drives, right? Yeah. So it's no longer mechanical, but it's still not nearly as speedy as actual RAM, right? But it's unlimited in the sense that you can go ahead and keep requesting as much memory as you want. When it runs out, you can't request any more. Right? But otherwise, it is much larger, right? It's only limited by the actual computing hardware. That is the memory, hard drive, etc. Right? It's not limited to simply just 4 megabytes or 8 megabytes or something like that. But it is generally less efficient. So it's no longer something that you have to do too much, but some gamer enthusiasts might do it occasionally. Have you ever heard, or have you ever done, or have you ever heard of somebody defragging their hard drive? Yeah? So what happens is files, when your hard drive fills up, files can be located on different parts of the hard drive, which means that this is the physical hard drive now, the needle needs to go from one area of the hard drive all the way to the other area when it wants to collect one file that has been fragmented along different places. Same thing can happen with a heap. You can have a chunk of memory here in the heap that belongs to you, and then then a huge big gap in some chunk of memory that over here that belongs to you. And for that reason, it's slightly less efficient. You pay a price for the much larger capacity. Right? That's true of everything, right? Really fast, really efficient stuff is also going to be really expensive, so you don't have too much of it, right? And less expensive stuff, hard drive space, that's nothing. You can get a 10 terabyte now, 5 terabyte. What? 20 terabyte hard drive, how much? All right, 200, how much? 200 terabyte, how much? 300 bucks, right? That's nothing. But try to buy the same amount of, 30 terabytes, you said, or 300 terabytes of RAM? Oh, wow. You're not even going to find a motherboard to support that, right? That's not even possible, right? So, it's generally less efficient, but it's much larger, and you're paying a price for it in terms of efficiency, okay? So, how do you allocate memory on the heap? Right? The answer is you ask the operating system for a chunk of memory. To do this, you use the function malloc, right? Which stands for, and here let me, memory allocation. There we go. Yeah, I got it. So the boldness there, the bolded things tell you what it stands for, memory allocation. It looks something like this. Here's its signature. I'm going to just cut and paste this to make sure I've got it right. There we go. So what are all those parts? In fact, we've got some new syntax here. For our purposes, size t can be treated as an integer. Right? In other words, you are asking malloc for n bytes of memory. Right? And so you pass it a number. I want 5 bytes of memory, or I want 1,000 bytes of memory, or I want 1,000,000 bytes of memory. Right? Generally, you need to compute the size of memory you need. Right? And to do that, you can use size of along with a variable. ... Let's just go ahead and look at an example here. Right? Let me go ahead and create an integer array. Int array is equal to, now I'm going to call malloc. We'll talk about this pointer here in a second. Okay? I need to request enough space, say, allocate enough space for, say, 1,000 integers. Right? Well, pull out my calculator and remember that an integer takes 4 bytes, right? So 4 times 1,000, that's pretty easy, 4,000. Right? You shouldn't do it that way. Right? Let the computer do at least some of the calculations for you. 4 bytes times 1,000 integers is 4 times 1,000. How many you want? That should be stored in a variable anyway, int n, 1,000. There we go. We've improved this now to 4 times n. I don't want to have to remember that 4. Because if I go back and change this to double or character or something like that, I'm going to have to change that 4. Right? I don't want to have to remember that there are 4 bytes. In fact, here's a dirty little secret of C, that the standard says that an integer only has to be a minimum of 2 bytes. You can go onto a really weird old system, and it'll end up being 3 bytes for some reason. Right? Modern systems will all be 4 bytes. I don't want to have to make all those guesses. So instead, I use the size of macro to determine how many bytes an integer takes. Size of int will then evaluate to 4, right, automatically for you. Take this code, move it over to a system where suddenly an integer is now 8 bytes, and you are future-proofed it. Right? You don't need to change it. You're letting the compiler do your work for you. Okay? So the size of macro along with a variable. Right? And I'll cut and paste that example in a second here. The malloc function returns a generic void pointer. That's the new syntax there, void star. Now just remember from pointer, when we covered pointers, how do I create a pointer to an integer? Int star a. How do I create a pointer to a double? Double star b. How do I create a pointer to a character? Char star c. Right? So what in the heck is a void pointer? Right? X. Right? So let me back up here for a second. And A can point to a memory location that contains an integer, 4 bytes. B can point to a memory location that contains a double, which is 8 bytes. A character is 1 byte. So what does a generic void pointer point to? Right? It just points to a memory location. It doesn't care if it's 4 bytes, 5 bytes, 1 byte, 8 bytes, 7 bytes. Right? It's just pointing to a raw memory location. And that's what a void pointer is. Right? A void pointer points to a raw memory location, not necessarily one that contains an int or a double or etc. Right? In other words, a void pointer can point to any type of memory location. Now let's think ahead. What if we didn't have this? Why do we want a generic void pointer? If I didn't have this, I would have to create a malloc function for integers, a malloc function for doubles, a malloc function for characters, and eventually when we define our own types, like an enumerated type or later on a structure, like a student type, I would need to reinvent the wheel and create yet another malloc, yet another malloc, create a malloc for every single type I introduce into the language. I don't want to do that. So instead, what we have is a generic memory allocation. Here you go, here's your pointer, right? There's your memory, the chunk of memory over there. What you do with it is your business. So if I create something that has 4,000 bytes, right? I could store 1,000 integers, or I could store 500 doubles, because a double is double the size. And I would be able to store half as many. Right? It's your business what you do with it. Since I want this to be integers, I will do a typecast to force it to become an integer. A generic void pointer doesn't know what it's pointing to. These 4 bytes, or these 8 bytes, or this 1 byte, right? By doing this typecast here, what I'm doing is I'm saying, no, you're pointing to a memory location that contains a bunch of integers, a bunch of 4 bytes, 4 bytes, 4 bytes, 4 bytes. All right? If I didn't do this, then it still wouldn't understand what I'm pointing it to. There are people who would argue that you shouldn't do this. They're wrong, because there are very good reasons for you wanting to do this. There are no good reasons for you not to do this. All right? Don't worry about it. If you want to read, I've got a citation for it if you want to read the arguments back and forth. For us, we're going to do it this way. Okay? Likewise, what if I wanted to allocate enough memory for, say, I don't know, 2,000 doubles? Right? So I would need a new variable here, m, 2,000. What would look differently? Or what would look different? Would I have an int star array? Not if I wanted doubles. What would it look like? Double star, and I've already used ARR, so what comes next? Cold burr, right? Double star, right? Malloc, size of int? No. If I've got integer, 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 I need double, double, double. And I multiply it by m. Awesome. Right? Now, remember that it failed when we wanted 10 million of these things. It's not going to fail anymore. I can set the first one to 42. I can set the last one, n minus 1, to 101, and I can print them out. First, last, r, %d, %d. And AR sub 0 and AR sub n minus 1. There we go. Remember, it's unlimited, not CPU time, but maximum memory size here. It's unlimited. And so when I run this, now it's perfectly fine. It does not result in a segmentation fault because I'm not filling up that stack space. Instead, what I'm doing is I'm allocating it on the heap over here. In fact, let's visualize that. Let's edit this code to no longer use a static array. Instead, let's use a dynamic array. Int star, call to malloc. You want 5 of them. How many bytes does an integer take? Size of int. There we go. There. Visualize this execution, and you'll see that when it finally comes up, the pointer exists in the main stack frame, but when I allocate it, it does not exist in the stack frame. That way, when I return from a function or go to a function, it still exists over here in the heap. Right? It's not destroyed when this stack frame gets destroyed. It's a pointer to this memory location over here. Now, when we covered pointers, I remember it pointing to one thing, right? That's not the only thing the pointer can do. Now a pointer is pointing to the beginning of 5 things, or the beginning of 10 things, or the beginning of 1,000,000 things, 10 million things, right? Still not going to be, I wonder what it would look like if I did 10 million. 1, 2, 3, 1. Right? It'll certainly work, but hopefully it doesn't crash my browser. It should be fine. Firefox, it would only crash this tab, and I can get rid of the tab at least. Yeah, it's not even going to do it. It's going to want to visualize this thing over here that is 10 million cells, and no, that's not going to work, right? But it certainly works over here. All right, 10 million, 100 million, 1 billion. I don't know if this will work or not. Let's find out. It does. Wow. How much memory am I trying to allocate here? Remember that this is 1 billion. 1 billion times 4, 4 billion. That's 4 gigs. Right? Is that even big data anymore? No. Right? What if I try to go up just a slightly bit more? Right, now that's 8 gigs. Okay, fine. Wow, cool. What if I go up to 4 billion? So 4 times 4 billion, that's 16 gigs. Let's find out what happens now. Okay, now we failed. Why? Not because we've run out of memory, but think about an integer. What's the maximum size of an integer? 2.147 billion. Can I hold 4 billion? Nope. What's going to happen? Wraps around, and I'm trying to allocate a negative 10,000 bytes? That doesn't make any sense, right? In fact, this would actually work. 8, 1, 2, 3, 1, 2, 3, 1, 2, 3, right? It'll actually work up to this point, right? Some point. It'll probably actually works up to this point, but only because the allocation failed. Right? Dot, dot, dot. How do I know when an allocation fails or not? So remember error handling. When you call a function and that function fails, it returns back to you. Except that this is returning a pointer, right? It's not going to return an error code. That's not how they designed the function. What is one value that we could definitely tell something went wrong, though? The one value that a pointer that we can check. An invalid pointer. Do we remember? You can check for invalid allocations because malloc will return ... What's the only thing it can return? What's the only invalid pointer that we know of? Null, right? There we go. It'll return null. And you can check for that. If array is equal to null, then we can say printf allocation failed. Not much we can do, ... because we've run out of memory or something. And then we'll exit on them. There. It's not that we've run out of memory here. It's that warning, that's way too big. All right, so overflow and conversion. So when I run this, the allocation failed. There's not much we can do. You can't allocate a negative amount of memory, right? I wonder what value that would be. Printf n is equal to %d in line n. I'm trying to allocate that much memory. Let's find out. Yeah, can you allocate that much negative bytes? Right? What would that even mean? I'm going to go ahead and that's downloading more RAM right there, right? Because I'm allocating a negative amount of memory. That means I'm giving it back to the operating system. I'm magically creating memory or something, right? So a void pointer can point to any type of memory location. Generally, you typecast it as the type of pointer you want, right? And upon failure, malloc will return a null pointer. Right? So you can actually test for that. Okay. Let me go ahead and get rid of that and just go ahead and cut and paste this into the notes. So, C. There we go. All right. So there again, there's no malloc for integers. There's no malloc for doubles. There's just one malloc. If you want to, you can also look up. I'm not going to cover them, but similar functions exist. You can have calloc, excuse me. I believe that I forget what that stands for. What does C stand for? It's not C allocation. Man, calloc. Oh, come on. There's no man pages in. There we go. Dynamic memory allocation that refers memory level. Blah blah blah. There's also realloc and free, which we'll talk about here in a moment. But there's realloc. There we go. For similar behavior. The key difference with calloc is that it does go through and zeroes everything out. So what it doesn't give you garbage values, it gives you 0 values. But you have to call it very differently. Realloc is a way that you can take an existing chunk of memory and either try to expand it or try to shrink it. Right? Again, what if happens if the expansion fails? Right? That you've run into memory that doesn't belong to you and it's not available. It'll return null. Question?
So if you're like allocating memory, do you reallocate?
Good question. Yes. And that's memory management. Right? But the key is that once you have successfully allocated, I should say, successfully allocated memory, you can use it like any other array. Any other. Can't type today, sorry. Any other array, right? Using square brackets and indices, right? Same problems exist if you try to access memory outside the bounds of your array. Undefined behavior, seg faults, etc. Right? Bad things will happen. Okay. So yeah, what happens? I'm just going to go ahead and demonstrate that we're not going to be able to do that one, but 1 million. There we go. And what I'm going to do is I'm going to put that into a loop. For int I equals 0. Actually, no. Let's do it in a while loop. While 1 forever. Do this. Allocate a chunk of memory and don't do anything with it. Allocate a chunk of memory and don't do anything with it. Allocate a chunk of memory and don't do anything with it. All right? So, GCC, run this. Now, we're not going to be able to see the effects directly. So what I'm going to do is I'm going to run this in the background. Right? Now, every nanosecond or however fast this program is, it's grabbing 4 megabytes, 4 megabytes, 4 megabytes, 4 megabytes, right? I did a million, right? Yeah. All right? So let's see it work. Do I have htop? No, I have, but I have, oh. All right, it ran out really quick. Let's go ahead and kick that down. There, just 1 kilobyte, 1 kilobyte, 1 kilobyte. It killed it because I grabbed way too much memory. All right, let me go ahead and try that again. GCC, come on. Run it in the background, and then look at top. There we go. So there's my, oh, it already died? Oh, come on. Did it, yeah, it already died. All right. I don't want you to do that. All right, fine. I'll do a trick here. 1 million? You're going to do this in your lab anyway. Sleep for 1 second. There we go. So what I'm going to do is I'm going to allocate 1 million bytes, 4 megabytes. I'm going to sleep for, let's go with only a half second. Those are milliseconds. And then it's going to wake up and try to do it again. Wake up and try to do it again. Otherwise, my program was just terminating way too quick. We weren't able to observe it. Right? So let's go ahead and run this again. Yeah, whatever. It exists. Oh, nope, not in the foreground. In the background. And let's look at top. User Ubuntu. No? Why are you not showing up? Where are you? A.out should be showing up somewhere here. All right. When we start next time, I'm going to do this on a different server where I've got some more more pull, and then we'll observe it there. Right?